Hello, and welcome to today's webinar, Wind Loading on Non-Building Structures. I'm Matt Brown, and today I'm going to be showing you how to apply wind loading to this structure here. This is from the previous webinar we had, which was about modeling non-building structures in RISA 3D. And so for today's webinar, our whole goal behind this is going to first to understand the wind code. Second, how we're going to apply the wind loading to this structure based off of what we figure out from the wind code. And that'll be both for wind and ice as well, because most structures like the kind I'm showing here are susceptible to ice loading, and that's something that many people haven't had a lot of experience with in terms of loading. So we'll show you sort of the ins and the outs of how to deal with that as well. Once we load up the structure, then we're going to take a look at interpreting the results from it. So let's go ahead and get started loading. For today's webinar, we're going to be talking about doing wind analysis and design per the latest IBC. That's the IBC 2015. And the IBC 2015 references the ASCE 7 2010. So whether you're on IBC 2015 or 2012 or even outside of the IBC altogether, the ASCE 710 is the code that you're most likely going to be dealing with. All of today's code references will be per that code. So let's start first talking about the wind loading that's going to occur on this structure. So when I take a look at ASCE 7, we can see it's very reorganized compared to ASCE 705, and the wind sections have all been split out into new chapters relative to the older code. So we'll start off at chapter 26. That's the first chapter that relates to wind in the ASCE 7. And 26 is general requirements that it's going to be talking about how we figure out common wind parameters that are applicable to all structures. So that would be things like risk category, your wind speed, the directionality factor. This is dependent on the shape of the structure. The exposure category, which is dependent on the site. The topographic factor, which is also dependent on the site. And lastly, the gust effect factor. So let's start at the top with risk category. So with risk category here, we would go to the table at the front of the code, and in this case, the non-building structure that we worked with previously was a large tank sitting on legs, and then it had sort of a lattice structure that was some sort of a conveyor system or the such that was probably loading the top of that. And so in this case, let's go ahead and assume that that tank, as opposed to being a water tank, is maybe holding some sort of hazardous chemicals at an industrial site. And so in this case, what we have to figure out is which risk category do we fall in? So there's 4 different risk categories, ranging anywhere from structures that pose no potential hazard to human life, all the way up to category 4, which is going to be structures that have a very high risk of human life in the event of a failure. And so what we see here under category 4, one of the options for falling under category 4 is essential facilities. Now, we would say that this tank holding hazardous chemicals is not what I would call an essential facility. Another option is that it poses a substantial hazard to the community. We can see here that this tank is at an industrial site, and so most likely if it fails, unless it's got some sort of sulfuric acid that's going to go gaseous in it, it's probably not going to pose any sort of hazard to the community just at that site. So we wouldn't fall under that either. Or it could be required for essential facilities to function. So this could be like a backup power facility for a police station or a hospital. Once again, we really don't fall under any of that. So we wouldn't call it a category 4. Now let's consider category 3. Well, one of the options is that it poses the substantial risk to human life. Now in this case, if this is just a chemical tank at an industrial site, I would expect that if it fails, it might kill 1 or 2 workers there. But other than that, it's probably not going to have any sort of widespread effects, so we wouldn't have to worry about that. Another option for category 3 is something that could substantially impact day-to-day life. Again, probably not going to have any impact other than right at that site if we have a failure. And then we have a catch-all category for hazardous chemicals, and those can fall under either Category 3 or Category 4. And the way the code describes that is that that category is going to be determined by the jurisdiction authorities. So in other words, we would have to talk to the county or the city or the state in this case and basically plead our case as to why we felt that our hazardous chemicals fell into Category 3 versus 4. In this case, we'll assume that we did get a Category 3 approval. And so in that case, our importance factor for wind will be 1.00. Next, let's talk about the basic wind speed. So for this, we're now getting into site-specific properties of this. So let's take a look at a fictional project site where this is occurring. We're going to assume that this is happening, that this structure is being built in East St. Louis, Illinois. And we have a zip code here as well, so that way we can zero in on the wind speed. And then in the next webinar that we cover, we'll be able to talk about things like the seismic effects at that site. So the wind speed for East St. Louis, when we're in a risk category 3 structure, is 120 miles per hour wind. Now, one important thing to keep in mind is that that's a strength design level wind. This is different from a service level wind, which was in previous codes. So if we wanted to compare this against ASCE 705, they would have called this 90 miles per hour back then. Now we're designing it for 120 miles per hour. But when we factor all the loads, everything will come out to be the same. The next thing that we need to talk about is the wind directionality factor. This factor is basically determined by how the wind hits and passes around all the different aspects of the structure. And because we have varying aspects of the structure, with this being a tank and then a latticework tower, we're actually going to have separate factors for different parts of this, and we're going to have to combine this all together to get a wind design for the whole structure. So we'll start talking about the tank. And in the tank, if we take a look in the code, we're going to find that our directionality factor is 0.95. That would be the factor that's applicable for round tanks, and in this case we're talking about smooth round tanks. For the tank legs, we have a directionality factor of 0.85 because those are what we would call lattice framework. And then similarly, the tower as well, that is also going to be 0.85 because it's lattice framework. Next, we'll talk about the exposure category at the site. So there are 3 different exposure categories. There's exposure category D. This is almost exclusively for coastal zones, and this is where we have a very flat surface such as water that runs at least a mile in a given direction. Now, compare that against exposure category B, which is what we would consider to be a urban or suburban site. And this is where we have a bunch of buildings or maybe a tree line that are all fairly close to the site, within a half mile, that are going to do a lot to block wind or keep high wind speeds from building up. And then we have the catch-all, which is exposure C, which is everything in between those two. So here's category D, category B, and category C, so you can see an explanation of which one of those are. Next, let's take a look at a site photo in this case. And so here we can see where this will actually be built. And we can see this photo was taken right from where this tank is going to go. We can see that we have the St. Louis skyline right over here, and that's got some tall buildings. Certainly the arch isn't going to be doing anything to block any wind, but those tall buildings conceivably could, although they are a half mile away. And then we have a tall bridge as well that's a half mile away. But the rule for exposure category B is that we would have to have pretty much all of these items in a radius of a half mile all the way around in order to count as an exposure category B. Now, by contrast, this certainly isn't an exposure category D, since I don't have a wide open flat area in any distance around. So in this case, we could safely call this an exposure category C. Next, we'll talk about the topographic factor. So if we take a look at the picture that we were just looking at, here we can see that we've got this levee on the river, and this levee is actually occurring over here on both sides of the river. So the question would be, does that pose any sort of a topographic effect for our wind speeds? So coming in here, if we assume that the levee is 10 feet high, and that there's an equal height levee on the opposite bank that's 1,500 feet away, we would have to check this condition for topographic factors. And one of the topographic factors is that on our site, we have to have no obstructions, other than, of course, this levee that we're talking about, within a distance of 100 times the height of whatever we're sitting on top of. And 100 times the height of it would be 1,000 feet, which is less than 1,500 feet. So therefore, we did meet this condition. But we have to meet all of the conditions for topographic factors in order to have to consider topographic in our design. So in this case, yes, the fact that we have basically that flat surface of the Mississippi River for at least 1,000 feet is going to be enough to have us meet that first condition. Next is the second condition, and for this condition we're saying that there are no obstructions of at least half the height within 2 miles. And so in this case we're talking about half the height of the levee, and if we assume that the levees on both sides of the river are of equal height, well, then that 1,500 feet, which is the width of the Mississippi River right there, is less than 2 miles, so therefore we did not meet condition number 2. At this point, we don't even need to go in and take a look at other things like condition 3, because we've already figured out that our topographic factor didn't meet all the conditions, so therefore it just defaults to 1.0. Next, we'll talk about the gust effect factor. So for gust effect factor, we need to figure out whether our structure is rigid or flexible. In this case, we're going to assume that the tower and the tank are actually not structurally connected to each other. So there's a separation in between those two. And of course, if they're structurally isolated from each other, then that means that one of them could be rigid and one of them could be flexible. Now, what is rigid versus flexible? Well, per the ASCE 7 wind code, what we're saying is that a rigid structure is one that has a fundamental frequency greater than 1 hertz, or in other words, a period of less than 1 second, versus a flexible structure, which would have the fundamental frequency less than 1 hertz. So we have this hard cutoff here of 1 hertz for whether or not we're going to consider each of these structures to be rigid or flexible. And we've got a little picture down here which helps to illustrate the structures so we can see what those look like. And so what happened is that I ran a dynamic analysis on this structure. Now for those of you who are wondering how to do that, you'll have to stay tuned for our next webinar, which is going to cover dynamic loading and analysis within RISA 3D. So for now you'll just have to take my word for it that I came up with this. For the tank and its legs, I found one fundamental frequency, which was at 8.4 hertz. Now, since that's greater than 1 hertz, we would consider that rigid, so the code allows us to take a simple gust effect factor of 0.85. Now, on the tower, what I found was a range of natural frequencies. Now, you might be wondering, how could there be different fundamental frequencies for a given structure? Well, keep in mind that this tower can have one frequency, say in the x direction, and one in the z direction, and even another vertical one for this cantilevered portion to be bouncing up and down. So I had to find all of the different fundamental frequencies for this structure, and what I found was that they all sort of fell into this range between 0.5 hertz and 0.77 hertz. And certainly all of them were less than 1, so therefore we're going to have to consider this tower as a flexible tower. So coming in here for the gust effect factor, it's very easy. As you saw before, we were able to consider a rigid gust effect factor of 0.85. For a flexible gust effect factor, all we have to do is just this simple calculation as outlined in the ASCE 7. And when we get to the end of this calculation, what we'll find is that our flexible gust effect factor is 1.272 in this case. Now I actually took this as an envelope between the lowest frequency and the highest frequency of all the fundamental frequencies in the structure to make sure that I was capturing the highest gust effect factor. Now let's talk for a moment about concepts behind wind loading. So one important thing to understand is what is the main wind force resisting system as that compares against components in cladding. So the main wind force resisting system, this is comprised of all the elements in the structure which are keeping the structure from collapsing during a wind event. And so anything that's critical to hold this structure up during wind is absolutely part of that main wind force resisting system. Now we would contrast that against components and cladding in the structure. And in this case, what we would be talking about is both structural and non-structural elements that are acting as a link between the wind and the main wind force resisting system. In other words, these elements are catching the wind and carrying it to our main wind force resisting system. But the important thing to know about components and cladding, so that you can help decide whether or not a given element is a main wind force resisting system element or a components and cladding element, is to consider, is that element essential for the overall structural stability? And so if we talked about a building type structure for a moment, certainly something like the braced frames or the diaphragms or the shear walls or the moment frames, those are all things that are holding the building up against those lateral wind forces. But if we talked about things like wall studs on the exterior of the building, well, certainly those do carry wind, but if a wall stud failed, would we have any concern about the whole building coming down? Probably not. That's what makes that wall stud part of the components and cladding. Now let's take a look at an example here where I have a two-dimensional frame. And what we want to do with this 2D frame is pick out what are the parts of the main wind force resisting system. So what I can see here is it's a 3-bay frame with pinned beams all along and pinned base columns, and then we have X bracing in this location. So then the question becomes, if I apply a lateral wind load right here on the frame, which one of these pieces in this frame are going to be helping to resist that load, and which pieces are just sort of along for the ride? And one of the ways that we can determine that, aside from visually guessing it, is to take a look at things like the reactions. So we want to follow the load path. Load path is the critical thing to understand whenever looking at things like main wind force resisting system and trying to figure out what's part of it. So what we can see right here is when I apply this load, all of the elements I highlighted in blue here are part of that main wind force resisting system. And we can see that the load path moves such that this applied load comes out as reactions down here. Now compare that to the base of these columns where there's no reaction. That's because all these elements in green here are just along for the ride. They would not be considered part of the main wind force resisting system in this case. Now you might think, all right, well, we're open and shut on this structure. Obviously, this is the main wind force resisting system, just the blue elements. But you would actually be incorrect there, because you have to recall that wind can also act from the other direction as well. And if we have wind act at this direction of the structure, well, in that case, then these beams right here are also critical to holding up the structure, because if they're not present, they can't transmit the force over to the braced frame, and so then these columns can get knocked over. And we can see right here where that force comes in and gets resolved down at the base of those columns. So therefore, really everything in this structure, except for these two columns right here, is part of the main wind force resisting system. Now, we've moved outside of non-building structures just for a moment so that I can clarify about components and cladding. So let's take a look at a typical detail from a building type structure, where we're taking a look at a cross-section of a building here, and this is the exterior, and we're going to say there's a brick facade right here with wind blowing laterally onto it. So if I have wind blow and hit that brick, the wind is then going to carry itself through the brick into this shelf angle that's up at the top and the bottom, and that shelf angle spans in between light gauge wall studs. And then those wall studs in turn connect to a main wind force resisting system beam right here and to a kicker brace that stabilizes the wall studs against this. Now if we consider this structure right here, certainly all of this could go away and we would still have overall stability against wind. And so if we were to superimpose that, this is what we would see in terms of this frame, the main wind force resisting system, with the components and cladding shown around it here. And so for the main wind force resisting system on this structure, looking at it, we have no cladding or facade whatsoever. We do have the tank wall, but that's made out of steel plates in this case. And basically everything in this non-building structure is somehow contributing to lateral stability. So we don't have a lot of extra pieces in this structure, and certainly with most non-building structures, you're going to be sort of at the bare minimum where everything in there is serving a purpose, and a lot of times it's going to be serving a lateral purpose. So therefore, we would say that for this particular structure type, there's no components and cladding load that needs to be calculated. Now, that's not necessarily true for all non-building structures. You can certainly have plenty of non-building structures where you do have to consider components and cladding, and definitely if I had, say, some corrugated metal siding around this tower, well then we would have to get into that. But for this particular example, we won't be, and instead we're going to focus on the main wind force resisting system loads. So let's take a look at what chapters those occur in. So first off, for main wind force resisting system, there's 3 different places we can look in the ASCE 7. There's chapter 27 that applies to buildings of all heights, but remember that right here we have non-building structures, so that one's not going to be applicable. There's chapter 28, and that applies to low-rise buildings, once again, not a building. And then there's chapter 29, and that applies to roof overhangs, parapets, and other structures. And I think we firmly fall in the other structures camp right here. So in order to have a wind load calculated per chapter 29, we have a number of preconditions we have to meet. Now, if we cannot meet these preconditions, then unfortunately we're going to have to go into another chapter, and that one requires things like wind tunnel testing. And wind tunnel testing is something I definitely don't want to have to do for this structure. So let's double check that we meet all the preconditions of chapter 29. So the first is that it has to be a regular shaped structure. The nice thing about regular shaped structure is that that is the extent of the definition of it within the code. So it's entirely up to you as to whether or not your structure is regular shaped. There's no sort of further guidance that you're given on that. I think it's regular shaped in this case. Next is no special response characteristics. We have no reason to think that this structure would enter any sort of strange response characteristics. And no channeling or buffeting effects at a site. So definitely if we were dealing with something like a suspension bridge, we all know from history that there may be some special characteristics, or there could be some channeling or buffeting due to the area where this is being installed. But in this case, right along the riverfront here in sort of flat Midwest, I'm not too concerned about any of that. So next we'll talk about the sections of chapter 29 that give us the final pieces that we need to calculate what the wind force is going to be. So we have the velocity pressure exposure coefficient. And so this coefficient here is based off of your height and based off of your exposure category. And what we find then is that that coefficient is going to be a value of 1.26. Next, we'll talk about the velocity pressure for the tank. And so for that one, we can see that we can take that kz of 1.26, our topographic factor, our directionality factor, and then the wind speed, and we can take all that to find our Q sub z value to be 44.1 psf. Now note that this is not the design pressure, this is just a base pressure from which we will derive the design pressure. So next, we'll take a look at what is that base velocity pressure for the tank legs and tower. And you'll see that all these values are the same here, except for the directionality factor, which we figured out was 0.85 for the tank legs and the tower. And so with that, we find that our wind pressure is going to be 39.5 psf for everything but the tank, basically. Now we have to figure out the force coefficient. And the force coefficient comes from a number of different figures that are in chapter 29, and one of them is for what's called a trussed tower. And in this case, I would consider both the tank legs and the tower we have here to meet that definition of trussed tower. In order to find the force coefficient, we need to know what the ratio of solid area to gross area is. And so what I did in this case was I measured the overall size of one of these bays on here, and then I calculated what the surface area of all the steel members would be in here. And so when I divided that, I got an approximate ratio of 0.17. And so in this case, I just picked a typical bay to use that for, and we don't have to get very exact with this number. I just want to get a ballpark number here that I can apply to everything, because it's not going to make a very large difference. Well, now when we take that 0.17 and we plug it in here to the force coefficient, what we end up with is a coefficient of 3.1. Now this is basically a multiplier accounting for the amount of wind load that's going to occur on this tower. But keep in mind that 3.1 is for the entire depth of the tower, and we'll see how that comes into play shortly. Next, we want to talk about the trussed tower over here. So we were just talking about the tank legs. And on the trussed tower, we will find that we actually have nearly the same ratio of solid area to gross area. It's 0.17 once again. And so we have the exact same force coefficient in this case, 3.1. And then we'll talk about the force coefficient for the tank. Now for the tank, that comes from a different portion of the code. This is still under Chapter 29, but there's a different table that we go to that's relevant to tanks. And so for this, we need to consider whether or not the surface of the tank is smooth or not. Now something that would not be smooth would perhaps be corrugated or the such, but in this case we're going to assume that this is made out of steel plate welded together, and that's considered very smooth per the code. And so if we say that the tank is up at 100 feet, which is actually the maximum height of the entire structure, but conservatively we're just using h of 100 for everything, and if we say that we have a 32-foot diameter, well, then we have to check that diameter ratio to figure out what number we're going to have to use. And what we find here is that that diameter times the square root of the wind pressure is 213, way larger than 2.5. So then the program tells us that we have to consider the h over d ratio, and this would be the overall height divided by the diameter of the tank. That's about 3.125. And so that gives us a force coefficient calculation coming out of the code of 0.54. So we can see that our force coefficient is much less for the tank than it is for the tower. And that's because this smooth round tank has the capability to shed a lot of wind off of itself that things like lattice work is actually going to catch and absorb. Alright, now that we have that part taken care of, we can actually figure out what our design wind pressures are going to be. So we'll start with the tank legs. Now with the tank legs, we have that base pressure of 39.5. We have our gust effect factor of 0.85. And because I'm going to be applying the wind pressure not just on one face, but I'm going to split it in between windward and leeward pressure, instead of using the force coefficient at its full value, we're going to divide it by 2, which will allow us to apply 52 psf to the front face of the tank legs and 52 psf to the back face of the tank legs. Next, for the tower, similarly, that's going to have 78 psf applied to it, and that is going to be because it is flexible as opposed to rigid. So we had that much higher gust effect factor compared to the rigid gust effect factor. And then for the tank, we can see right here we have this very low force coefficient, and so in this case we're way down at 20.2 psf is the design force for that tank. Now let's take a look at the wind load cases and how we're going to apply this to the structure. What you'll see here is we have the standard case, which is case number 1, and that's just wind blowing dead on right onto the structure. Now if we take a look down here at case number 2, this is what we would call our accidental torsion wind case. And the idea behind this is that the wind load may not be lined up perfectly centered on the structure, and if there's an eccentricity in the wind load, it's going to cause the structure to have somewhat of a torsion in plan view. Keep in mind that these images I'm showing right here, we're looking down on the structure, so this is in plan view. And considering this accidental torsion is very important because we may have a structure that has a torsional buckling problem with it. And certainly something like this water tank could be the case where we could have it very strong for vertical and lateral loads, but if we started to twist or rack the entire tower, it could fall apart very quickly. So it's very important that we do consider this torsional load as well. Now, case 3 is what we would call our quartering winds. And this is where we have wind blowing from both directions on the structure at the same time, as opposed to a single direction. So we're going to have to be sure to apply this in the model, and we can actually do that just using load combinations. We don't even need to create additional load cases, and I'll show you how to do that. And then lastly, we have case 4 down here, and this is where we have quartering winds acting in addition to that accidental eccentricity. So this is just one extra case that we're going to have to be sure to check. So we've got our straight wind, our quartering wind, and our torsion. These are the three different basic types of wind that we need to do on here. So let's take a look at the tower. So for the tower, when we're going to calculate what the torsion is on that one of the things is that this is dependent on this dimension b, which is basically the width of the structure. Now in this case, we don't really have a clear answer for what b is. We might be able to consider the centroid of the overall shape, but in this case, I want to make sure that we're just capturing the worst case. So what I'm going to do is I'm going to use the full width of this tower, even though I know it's going to be conservative, just because I don't want to have any concerns about this not being torsionally stable. And so we would then consider that the wind is going to act at an eccentricity of 0.15 times b, or in other words, at 5.25 feet away from the centroid of the structure. Now the torsional moment that needs to be applied to this structure is just the wind force multiplied by that eccentricity. And so in this case, this would end up being the wind force multiplied by 5.25 to give us a moment in foot-pounds. Now we could apply that in a number of different ways, but in terms of applying it to the tower here, if I want to capture a torsional effect, one of the easiest ways I can do that is to put a big fat point load right out at the end of this tower, and what that's going to do is twist this whole tower, and it will be resisted as a torsion right down there at the base. So this would be the most conservative method. Certainly we could do a distributed load along here, we could move this load in closer to the center, but in this case, let's go ahead and calculate what it would take to get the required amount of torsion acting way out at the end here. Well, to do that, we would just have to apply a force that's equal to that torsional moment divided by the full width of this tower, which is 30 feet. And that gives us 0.175 times F. So that will be the force that we apply out there. Next, let's talk about the tank. So on the tank here, this is round, but we want to be able to induce a moment so that we can twist this whole tank on its support legs and therefore get all the support legs to try to fail, so we can sort of get a worst case scenario here. Well, on the tank, the diameter is 32 feet, and so 0.15 of that is 4.8 feet. So what we're pretending is that this force is acting at an eccentricity of 4.8 feet from the center of the tank. And so then we're going to take that torsional moment, which is the F times the eccentricity, which would then be equal to F times 4.8 foot-pounds. And what we're going to do with that is put a line load all the way around this tank, around its circumference, and that's going to be acting tangentially to it, and that's going to put that twist onto the structure. So now that we've talked about this a little bit, let's see how we can actually apply all these loads within RISA. So I'm going to open up the RISA 3D model here, and what we see is this is the non-building structures model, and we're picking up right where we left off from the last webinar on this same model. And if I come into my basic load cases here, what I can see is that this model is already predefined with a few different basic load cases. So we have the hydrostatic pressure, dead load, live load, and then the fluid weight as well. Now coming down here, what I want to do is set up a few different additional load cases, and these are going to be specific to the wind loading. So I'm going to set up one that I'm going to call wind X, one that I call wind Z, and then we'll say that torsion is a wind about the global y-axis, that's the vertical axis, so for that reason I'm going to call that one a WLY. Here for the name, I'm going to call that torsion. So for wind X, for the category, I'm going to choose WLX. For the wind Z, I'm going to call that WLZ. And for the torsion, I'm going to call that WLY. Excellent. So now I have these three load categories chosen. And so at this point, we're now ready to set up applying the wind load onto the structure. So let's begin with the tank legs. So on the tank legs here, I want to apply the wind load in the X direction. And so in this case, I'll go ahead and apply the loads always in the positive direction. But let's consider something here. If I come up here into a plan view and take a look at this structure, what I see is that I don't have anything that aligns with the global X or the global Z directions. In other words, this whole structure is somewhat skewed. It's at a 45-degree angle from any orthogonal global axes. having this skew actually is not very useful for me in this case, because I want to be able to consider wind acting perpendicular to these surfaces. And in order for me to apply wind acting perpendicular, I'm going to have to break it into components, apply those separately. That's a lot of work that I don't want to deal with. So one thing that I might do here is I might take this whole structure and just rotate it so that we then have the structure aligning with the global axes. Up here, I'm going to turn on the graphic editing toolbar and come over here to move via rotation. So this tool will allow me to rotate the entire model, and if I click on that, I can come up here and say rotate the whole model about the global y-axis by 45 degrees, and then I'm going to specify the coordinates as 0, 0, 0 for the center, and I'm going to hit apply. And so what we get now is a structure that lines up perfectly with the x and z directions, making it much easier for me to apply the wind loading here. So next I'm going to snap myself into an isometric view, and let's come over here and take a look at the tank, and I want to isolate only the tank legs in this case. So I'm going to snap myself here into an elevation view, and this will allow us to get a closer look at things. And I want to come in here and grab nodes. These nodes are going to be snap points for me, and so they're going to end up being very important. Those will be up at the top and the bottom. So now coming back into an isometric view here, let me make sure that I have all the nodes selected that I'm going to need, and that looks like a sufficient amount of snap points. Now what I'm going to do is use this tool on the left here, this padlock tool, to lock everything else out, so that now we are only taking a look at the tank legs. And what we know from our wind load calculations already is that the tank legs need to experience a pressure of 52 psf. And I'm going to have that always act in the positive direction. So I'm going to come up here to apply area loads. And you'll see under area loads that one of the options that's in here, if we choose wind X here, is a open structure area load. And what that open structure area load is going to do is that's going to apply the wind load according to the size of the member. So in other words, wind load is going to blow through this structure. When it hits members, it's going to apply that load as a function of the shape of the member in that case. In terms of the dimensions perpendicular to how the wind is blowing, and it's not going to consider any shielding, and we'll see how that works. So coming in here, I want to say that's acting in the global x direction, and its magnitude was 52 psf for the tank legs. That's 0.052 ksf. And I'm going to draw a polygon right on here, and so now we can see what that is. That wind load is going to blow through here, and it's going to apply itself to everything. Well, how can I see how that works? I mean, certainly we could try to just take the program for granted that it's going to do things correctly, but I want to have a good idea that it's going to be attributing the wind correctly. Well, for that, I'll go into the load combination spreadsheet, and I'm just going to create a quick dummy combination which references that load. Now I applied that load as part of the WLX category, so I could just create a load combination which is just WLX with a factor of 1. And if I solve that load combination, what we're going to see here is that a new temporary load case called the transient area loads gets generated. And when we have that, now we can graphically see how that load was applied to everything. And so we see here we have a line load running on all of these members here, and we can see the magnitude of it. So for example, it's 0.31 down here at the base, going up to 0.027. So that's about 27 pounds per linear foot of load that's occurring right across here. And if I double click on this member, this is a 6-inch deep double angle, and let me render it so I can take a peek at it. Alright, so taking a look at that 6-inch deep double angle, if we have a load that is about 52 psf blowing on something that's about 6 inches, we're going to have something that's about 27 pounds per linear foot. And you'll note that even though I drew this load acting only right here, it blew all the way through the structure and hit everything behind it right over there. So therefore, we're picking up that load just that way. Next, I'm going to come in and put in my z direction load as well for this tower. So I'll come up here to draw area loads, and we're going to change that to wind z, and it's blowing in direction Z, but the same magnitude. So now at this point, I've applied both my X and my Z for the tank legs. All right, now the next thing that I want to do is apply the wind load to the tower in this case. And so for that, I'm going to snap myself into an elevation view once again. And here's something important that we have to consider. We're actually going to have some unintentional wind effect due to this wind X that's going to occur on the tower over here. Note that if I solve and take a look at my transient loads, that wind is actually going to blow right on through the tower legs and hit our tower as well, the tank legs, and hit the tower. So here we're seeing this wind load is hitting the tower. If I go ahead and apply the wind load that the tower requires in addition to the wind load that's on the tank here, what I'm going to be doing there is I'm going to be double dipping, and we certainly don't want that. So for everything here and down on the tower, what I actually want to do is apply a wind load that is just the difference between the required tower wind load versus the tank leg wind load. All right, so for a wind load that's acting in the positive X direction, this is the plane where that's going to act on this tower. And so we found that our design wind force was 52 psf for the tank legs. It was 78 for the tower because the tower is flexible. And so that's a 26 psf differential. So coming up here, I'm going to say that we have a wind Z in open structure, and that I'm going to add an additional 26 psf of wind. And sorry, that's in the X, not the Z direction. I'll click on these points here, and here we have this extra 26 psf of wind load that's going to be acting. And then now I'm going to come back into that elevation view, and I am going to grab the rest of this. So we certainly don't want to grab the tower here, or the tank, but we do want to get the tower. And I'm going to use the padlock to lock the rest of that out. We'll snap into an isometric view. It'll be a little bit easier to see in this case. So let me activate snap points. And I want to apply now the full load up above here, because we're no longer talking about an open structure load that's passing through these tank legs. We're now just talking about loading that's going to apply on the tower. And so that's going to be at the full 78 psf that we have. So clicking along here. There we have that. And then we can't forget this upper portion of the structure as well. So now I've applied all my wind load X to the tower. The next thing I need to do is apply the Z wind load, and this will be a little bit easier since in the Z direction we don't have any interference between the tank legs and the tower. So coming up here in the Z direction, I can actually reselect the entire model, and we can do this just as 2 points. So I'm coming up here with my open structure load, zooming in on the points where I need to click, and here we see the open structure load applied to the main portion of the tower there. And then all I have to do at this point is apply this as well to the part of the tower that sticks out. So we'll grab this node, that one, and that one. All right, excellent. So now, coming into an elevation view, we can see there's our wind load applied to all of those. Excellent. So the next thing that I'm going to do is apply the wind load onto the tank. And so if we're going to do it on the tank itself, what we're going to do this as is a surface load. Now the important thing to understand is that the code tells us that we need to apply this load onto the projected area of the non-building structure in question here. And so in this case, what we would want to do is apply it just projected onto the area that we can see here in this elevation view. To do so, I'm going to select all of the plate elements that make up this tank, and I'm going to take us up here into a plan view. I'll shut off the display of nodes, and we're going to come up here and use the surface loads. If I come up here to the plate surface loads, and we go and choose the wind X, what I'll see is that I can apply this in the PX direction, so that's projected in the global X direction, and we will give it 20.2 psf total, so that's 10.1 psf on each face, so that's 0.0101 ksf. And when I hit apply, what we'll see here is that this wind load is projected such that when the wind load is blowing straight on in the x direction, perpendicular to the tank, it's up at that full 10 psf, but that load actually tapers down to about 0 as the wind is tangentially blowing past it, since of course we wouldn't really have any wind due to friction or anything like that. Next, I'm going to come back in here and I'm going to create my wind z, and so I'm going to blow that in the projected z direction. And so for that, that will be once again 0.0101 and hit apply. So now we have the wind load acting in this direction as well. All right, and we can sort of see right here the direction that that wind is facing on the tank. And then lastly, we cannot forget about our torsional wind as well. Now, in order to know the torsional wind, what we're going to have to do is we're going to have to know how much wind is carried by, for example, the tank versus how much is carried by the tower. And so, of course, it's going to depend on those levels of force. Let's start off with the tower here. What I'm going to do is select only the boundary conditions that are at the base of this tower. Now, we have two different structures here. So what I can do is grab only these boundary conditions, and of course we know that all wind forces that are applied to this tower here are going to resolve themselves at these 4 points, and I'm going to solve this in the WLX direction. And then I'm going to create a second load combination that would be WLZ. So if I solve for WLZ, what I'm going to do is take a look at the joint reactions. But my problem with joint reactions is that it's going to apply for all the nodes in the structure, but I really only want to know the reactions that are just for these points down here. So out in the model view, I'll click the white exclude button and hit yes, and this is going to come back and give me my total force in the z direction in this case, or the x direction, depending on which way I solved it. And so what I see here is that for WLZ, what we end up with is about 14.3 plus 7.49. So we end up with about 22 kips of z direction wind load in this case. Now if I solve for WLX and we do the same exclude on those nodes, what we're going to see is we get 4 times 7.8. That's about 31 kips. So obviously we're getting more wind load in the x direction than we are in the z direction. So we will conservatively use the total x direction load that's occurring on this tower. And what we recall is that that is going to be multiplied by 0.175 in order to find our torsional point load. And so 31.2 kips times 0.175 gives us a point load that we're going to apply that will act torsionally here. And I'm just going to click on the node where that'll be applied. And that's going to be 5.5 kips. So I'll come up here for torsion. And then we're going to say that this is acting in the positive z direction of 5.5 kips. And so we've put that on there. So that point load right there on that tower is going to twist it. Now the next thing we need to do is consider the tank in this case. So let's come back over here and grab only the tank boundary conditions. And I'm going to solve for my WLX and hit exclude. And so what we can see here is that for the tank, our wind force is about 4 times 20.5. That's about 82 kips of wind force that's on this tank. And what we saw was that the torsional load that we need to apply on here was 0.003 times that value. And so what we're going to end up with then for a torsional load is about 246 pounds per linear foot needs to be applied around the circumference of this tank. So if I grab just these members that run around the ring of the tank here, I can actually come in this case, and I can say this is part of our torsional wind load. It will be in the local x direction. That would be basically an axial force on each member. And we're going to say it's 0.246 kips per foot. So if I apply that on here, here we see here's this ring of 246 pounds a foot that's going to twist that whole tank. And so that's going to then account for the torsional wind loading. All right, so at this point, the wind loading has now all been applied to the structure. Let's go back for a moment, and let's talk about ice loading. So in this example right here, we're going to have to go back into Chapter 10 because we're in the Midwest and you can get icing effects on these lattice-type structures in the Midwest. And so under Chapter 10, we're going to have to calculate the atmospheric icing forces. For that one, we have the following parameters that we need to calculate. We have risk category, we have the nominal ice thickness, the height factor, the topographic factor, the concurrent wind speed, and that would be the maximum wind speed that we could get during a freezing rain event. And then we have the approximate diameter of the member, because of course the amount of ice that forms on a member is a function of the size and shape of that member. So in terms of risk category, we already know that we're in category 3, and so our importance factor is 1.25. The nominal ice thickness comes right out of a map in the book, and that tells us that in the St. Louis area, we have 1 inch of design ice thickness. Now for the height factor, we've just been taking 100 feet for everything, because that's the highest point in this structure. If I really wanted to get into nitty-gritty, I could actually have different height factors for different locations along the height of this, but we want to get a quick and easy design. So for this one, I'm just going to use that 100 feet. And then what we're going to see here is that the height factor, based off of that, is going to be 1.12. And for the topographic factor, that comes right out of the wind, and we already know of that as 1.0. Next, we'll figure out the design ice thickness per the ASCE 7. And so what we're going to find that to be is 2.8 inches. And then we take the design ice density, gamma, and that's 56 PCF. And then next, we're going to take the concurrent wind speed. This also comes out of a map in the book, and we see here that that would be 40 miles per hour would be the maximum wind that we would get during a freezing rain event where ice would be forming on these lattice structures. And then we take a look at that to figure out our design velocity pressures. Well, we've already run these calculations earlier for the wind pressure, and so we can see for the tank that's 4.9 PSF, and for the tank legs and then the tower that's 4.4. So right away we see that our wind forces are much lower during an ice event than during a full wind event. And of course that's because these ice pressures are a function of velocity squared, and 40 miles per hour versus 120, when you square it, makes a big difference in the total magnitude. For the concurrent wind speed with that 40 miles per hour, we've now calculated all of those values so that we can now figure out our design wind pressures. So for the tank legs, we put in that gust effect factor and the force coefficient. We get 5.8 PSF. For the tower, we get 8.7 PSF. And for the tank, we're going to get 2.25 PSF. Now, the important thing to consider is that when ice is on there, the size of the member won't be enough in terms of applying that load, because we actually have to consider how much bigger the member gets when we have ice on it as well. And so we're going to actually have to hand calculate the approximate size of each member for each member diameter. And so for that, we need to have a list of shapes that we have currently used in this model that are susceptible to icing. And so that would be the W24 by 76 tower legs, the double angle 6x6s that we have that form up the bracing on the tower, and then the tower itself, sorry, those are the tank legs that have these members. The tower itself has HSS 4x4 members used for everything. And so taking a look at the tank legs, we can see here with the W24 by 76, the approximate member diameter, and this is what we use to figure out how much ice forms on it, is about 25.5 inches. For the tank leg bracing, that's these double angles, and so for that one, we actually have to take a look at 3 different potential dimensions that we could have that could control. And so in this case, actually our controlling value ends up being the 6 inch plus 6 inch equals 12 inches on here. And then for the tube, for a square tube, it's just going to be diagonally right across here. That'll be our maximum diameter. That ends up being 5.7 inches. So what I can do now is use this formula right out of the ASCE 7 to calculate what the weight of the ice on the members would be. And that's just gamma times the ice thickness and the diameter of the member. And so what we find is that that weight on the W24 by 76 ends up being just shy of 100 pounds per linear foot. That's a lot of ice. And we can see even on the L6 by 6 and on the tubes, we still have quite a bit of ice weight, and we're going to have to apply that onto the members. Now for the tank itself, that can also pick up ice weight as well, and so we can calculate that out to be 41 psf of weight of ice that's going to be sitting on that tank. So for the members, what we're going to do is we're going to conservatively assume that the wind is always acting perpendicular to that D dimension that we took a look at earlier, that sort of diagonal dimension across there. And that's going to allow us to calculate what that force will be. And so we can see that the wind on the members, using the wind pressure times the size of the member diagonally, plus 2 times the ice thickness, because remember ice can occur on each side of it, is going to come out to be the following loads here. Now for the tank, the fact that we have ice on it versus not won't make much difference. We have a 32-foot diameter. With all of the ice on there, we have slightly more than that one. And therefore, we're not going to have to apply the wind load in any special way to the tank. We're going to conservatively say that the size is close enough that if we just apply the standard wind load that we need for ice on the whole tank, that's good enough. So let's go back into the model here before we get into the load combinations and apply those values. So in the model here, what I'm going to do is unselect the entire model, and then I'm going to use my criteria selection tool here to grab various elements. So for example, I can grab the tower column elements and hit apply. And then I can grab the tower brace elements and hit apply. And the tower beam elements and hit apply. And what that's done for me is this has grabbed all of the elements in my tower. And all of these elements are tubes in this case, 4x4 tubes. So they're all going to get similar ice loading. Well, I have to set up 2 different load cases in this case for ice. So I need to first off have ice weight. And so for that, I'm going to set up a load case that uses this IL. I know it says impact load, but we can use this for whatever we want. We're going to call this ice loading for us. And then I have an ice wind X and an ice wind Z, because of course this is a different magnitude than the regular wind design. So for the ice wind X, I'm going to use a category that's sort of out of the box here, WLXP1. And for the ice wind Z, I'm going to get WLZP1. So we'll come in here and find that value. Perfect. So we have those now set up with each other. Next, I need to apply the loading. And so what we know from the previous calculations is that on these HSS 4x4s, the weight of ice is going to be 29.1 pounds per foot. So if I come up here to ice weight, I'm going to say that acts in the global Y direction, so it's vertical, and that's negative 0.0291. And then hit apply, all selected. Now this whole thing is loaded up with ice weight. And then we just have to apply the ice wind. So the ice wind in the X, in the global X, well, that value right there was 8.3 psf, so that's 0.0083. And we apply that in the X. And then we come back up here to ice wind in the Z, and that's going to be the same magnitude as well. So now I hit ice wind in the Z. There we go. All right. Next, we need to get the tank legs and the tank lattice work. So I'm going to unselect the entire model, and I'm going to come back over here to the criteria select. And we know that the tank leg size is a W24 by 76. So I'm going to tell the program to grab all the W24 by 76 members. And we know that the weight on those ones, if I come back up here to ice weight, in the global Y direction, that was negative 0.0968, 96.8 pounds per linear foot. And then I can apply the ice wind X once again. That's capital X. That's 0.015. And then the ice wind Z, and that will also be 0.015. And then lastly, we're going to grab that tank lattice work here, the L6 by 6s, and we'll come in here and do the same thing. Come up to ice weight. Global Y is going to be negative 50.6. And then we come up here and say that the ice wind on that one is going to be a positive 8.5. And that's going to apply in each direction. So we come up here to the Z, and we apply that to that direction. And then the final step will be to apply the loads to the tank in this case. And so then we come up here to the tank, and we will select it. And I'm going to come up to apply the ice weight. Now for the ice weight in this case, I'm going to go to apply surface loads, and we're going to come up here and say ice weight in this case is going to be in the global Y because ice can form over the entire surface of this one. And we figured out that that was going to be 41 psf of ice weight applied on there. And then for the ice wind in this case, we figured out that this would just be the same wind load in this case in terms of magnitude. And so coming back to that one, that magnitude was 20.2. And if I take that one and divide it out, what we're going to find out is we have about a 2.4 psf wind load that we need to apply to the tank. And for that one, instead of going ahead and applying that one as a new wind load onto the tank, I'm going to do an interesting trick here. What I'm actually going to do is grab the surface loads from the tank from a different load category. So I'm going to go from WLX, from just our standard wind X, and I'm going to say I want you to copy only the surface loads from wind X into ice wind X. And then I'm going to say do the same thing here in the basic load cases from wind Z into ice wind Z. So this is a quick and easy way for me to not have to go ahead and reapply all these loads here. And so now I can come in here under the surface loading, and I can just click and highlight this whole column for ice wind X, and I can fill this in with the correct value, which is going to be about 2 psf. So I say 0.002 and fill the block on there. So now we have our reduced wind load in this case applied to the tank. So now coming back to the whole model, what we see is that I have applied a wind in the X and the Z. I've applied a torsional wind to this structure. I have the weight of the ice, and then I have the wind on the ice in the X and the Z. So with all that loading applied, the last thing that I need to do is take care of my load combinations. So we're going to do the design of this per AISC ASD, and that means that we have the following combinations. We have just dead load here. We're going to have dead plus live plus ice in this case. And looks like my slide got a little out of order there. There we go. So number 3 is going to be dead plus ice plus wind. Just dead plus wind in this case. Dead, live, and wind. And then these are overturning cases down here. So this is actually 0.6 times dead plus wind. And so this is going to try to check and make sure that this isn't going to become unstable or tip over. So we have to have all of these load combinations right here. Now, what's funny is, in this case, I'm just referring to wind right here as W, but we actually have quite a few permutations in this case, because we have to take a look at each case where W is applied. So we need to consider, can wind act just in the X direction, just in the Z? Of course, we have the quartering wind we discussed, and then we have that working in the opposite direction, and then we have that eccentric torsional wind in the straight direction and the opposite, and more, and more, and more. As you can see, it quickly becomes quite complicated how many different loads we have to apply in this program. And then in addition to all those ones, well, I mean, we need to come in here and figure out our ice wind as well. Now, figuring out how the eccentric torsion load is going to happen for wind on ice is rather tricky, and in reality, with these very small wind loads that we have, it's not going to make much difference. We're talking far less than the full wind load. So therefore, I'm making a judgment call and saying I'm just going to ignore the torsional effects when we have wind on the ice. And so then in that case, we do have things a little simpler down here in terms of where we need to apply all of those. Now, how do I handle all of these load combinations? Well, what I found is easy to do is actually to use Excel for this purpose. And so what I'm going to do here is go ahead and open up a spreadsheet that I sort of pre-created in this case. And this spreadsheet already has all those different combinations figured out. So if we come back here for a moment, when I talked about all of these different wind load cases, you can see in this spreadsheet that I've created here ahead of time that I have all these. There's WLX, there's WLZ, there's quartering and the opposite, and there's the torsional, and there are even the ice cases that we have here. And so now coming back just a little bit, I want to create my basic load combinations, and so I can set these up actually directly within here. So I can say that we're going to have dead load with a factor of 1. And let's back out here so we can see these side by side as I create them. All right, so I'm going to have dead load with a factor of 1. Now you'll note I'm not using the load combination generator. Some folks would use the LC generator in this case, but for me, it's not going to capture all these different torsional effects and ice effects that are in there. We don't have that built in and automated. This is where sometimes you need to be able to take the load combinations by the reins and get in and work with them. So here we have dead and live, and we have ice load with 0.7, and then dead, and then no live load, we have 0.7 ice load. And then this is where we would grab the wind ice. And so instead of just having one combination, we would actually say that that applies to this combination 4 times over again, just as we see right here. Now I need to make sure that these numbers don't change, so I want that to stay 1 for everything, and I want that to stay 0.7 for everything. And so you can see where Excel makes this really handy because, of course, with the spreadsheet nature of the program, I can copy and paste into Excel and cover all these different scenarios. So coming up here, let me grab all the normal wind cases. Here I'm trying to represent dead plus or minus 0.6 times wind. And so then I just come up here and copy those values, and we put them in this case. Now note that that's 0.6 times wind, and here I'm using 1 times wind. You're going to see how I work around that in just a moment. All right, next up we have dead load with a factor of 1, live load with 0.75, and then we're going to have that 0.45 times wind. So I'll come back up, grab all these different wind cases, and paste them down here. Now this should stay the same. And so this would be uniform regardless of all of these. So now I've created that combination right there. And then we're going to come up here and do the 0.6 times dead. So this is dead load with 0.6. And then 0.6 of wind. So once again, I'll grab all of these standard winds, paste them in here. And then we can copy these all down to there. And then lastly, we have the dead load, which is 0.6. We have the ice load, which is 0.7. And then the ice wind loading combinations, which are right here. I'll grab those ones. And then we want to copy these down. So now I should be able to copy these in place. At this point now, on these lines of my spreadsheet right here, I've basically recreated all of these combinations. What this will allow me to do is actually copy this, and I'm going to go into RISA 3D in the load combination spreadsheet, and I'm going to paste this in here in my load combination spreadsheet. And so what I want to do is start that over here at the BLC column, and we see that this now fills in nicely. And so this is something that I like to do to try to keep the loads organized so I can see them more clearly. And we don't actually have to have any names for these combinations in this case. And so then the last thing I need to do is actually put in the factors on the wind. And so for the wind factors, what we're going to do is come up here to take a look at our dead plus ice wind cases that we've got going on. And scrolling through here, I appear to have them right up here. And so when we apply that ice load, if I come back into my PowerPoint, remember that's supposed to be applied at a 0.7 on the wind. So what we can do is come up here and use this math on block feature to multiply this by 0.7. And the same thing here. I can do a math on block of 0.7. Now for the next group here, what I want to do that is a 0.6 factor. So I'm going to come up here and do a math on block to get that down to 0.6 of what it was. And I can continue to do this for all of these columns here. So I'm going to multiply that one out as well. The next group here where live is also acting, this in this case gets multiplied by 0.45 per the load combination factors. And so we can see how easy that is to get in there. And multiply that in. And then we want to come back down here to the last few groups. And so in this case, this wind, once again, is going to be at a 0.6 level for here, here, and here. And then these ones, if we just go back and take a peek real quick, that's going to be 0.7 for these. So you can see how we can put that one together. And 0.7. Now, all these combinations that I've created right here, these are all with wind load acting in the positive direction. But remember that wind load can also act in the negative direction. So what I need to do is copy all of these, and then come down here and create a new line, line number 47 in this case. I'm just keeping track. And scrolling down here, basically everything below 47 in this case, I need to multiply all the wind forces by -1. So I'm going to say -1 for those. And for these ones. And then lastly for these ones as well. So I've now multiplied all those by -1. And what you see here is that we end up with 90 different load combinations. Now this may seem like a lot, but according to the code, we actually have to solve this model for all 90 of these load combinations in order to get a design. So at this point, I would now come in here and choose solve. And I would turn on P delta. I'm just doing that by doing a fill block and saying yes. And then this will allow me to solve a batch and envelope solution of the model. Now, of course, because we're running over on time here, I won't make you sit through this entire solution. Now at least you've seen the general idea of how we would apply all these different wind and ice load cases and how we would put the combinations onto the model. All right. So, that concludes today's webinar on ice loading and wind loading within here. Keep an eye out for our upcoming webinar, which is going to be the third part of this series, where we're going to take this same structure and do a dynamic loading on it. And so this is going to finish up our non-building structures in RISA series that we've been working on.